So, hello everybody. Welcome to my disgustingly unprofessional talk on the limits and weaknesses of deep learning. So, my name is Connor, or as you may know me, I'm a computer science student at the TU in Munich around here and have very impressive credentials to show, unfortunately. Before we get started, I want to give a small little disclaimer here. I am an AI guy. I am not really a statistician, not really a mathematician, so my talk is going to be biased a little bit towards that direction of like what is interesting from an AI, general learning, machine learning perspective, just so you know. Also, worth mentioning, this talk is a little short. When I first picked this topic, I made a grave mistake, I think, in underestimating just how much there is to talk about. This is a really big topic. There's lots of really interesting work I would love to talk about. I had to distill it a lot into what I find most interesting key points. I hope it's still going to be really interesting to all of you. So, deep learning is hype. I don't have to tell you guys about this. Front page of Nature hype. From Google's AlphaGo system to your day-to-day work in image recognition whatsoever, self-driving cars, which are becoming more and more a thing. We hear these stories of millions of miles driven without a single accident. Really exciting stuff. I don't know if you guys heard about this one. This I thought was really interesting, where OpenAI actually made a bot that could beat esports pros at Dota 2, which I find more interesting actually than the AlphaGo system, because Dota is a much more complicated, more free-form domain, and I was really impressed that they could make it happen this quickly. So things are happening fast. There's a lot of hype around it. But is it overhyped? This is the kind of controversial question I want to talk about a little bit here. Deep learning is made of two parts, basically. The backpropagation algorithm and the concept of artificial neural networks. The backprop algorithm itself dates back to a paper co-authored by Hinton in 1986, while the concept of artificial neural networks, or at least their predecessor, the perceptron, it dates back even to 1957. And they've changed somewhat, but not really since then. Well, an algorithm being old, or a concept being old itself, isn't disqualifying in any way. Back then they didn't have the computational power to do a lot of the really interesting things we can do nowadays. But I'm not the only one that's been feeling a little skeptical, a little hesitant lately about what's been going on. Hinton himself has recently remarked that he is deeply suspicious of backpropagation, going so far as to even say, my view is throw it all away and start again. That's a pretty big statement. That's from basically the guy who started this whole thing to a large degree. So what could make him say that? Well, that's what I want to talk about today, at least brief a few of the things that could make you suspicious of these algorithms. So I want to describe some of these noteworthy, interesting problems that seem to be impossible to overcome in some way, that appear in this kind of backpropagation-based learning. And I don't want to go into the nitty-gritty of like the mathematics or anything like that. I want to give you, if possible, an intuitive feeling of what is going on here, why do these things happen, and when should I be aware of them, perhaps for my work. And importantly, I want to burst a little bit of the hype going on, especially in the media. This here, for example, is one of my favorite examples, where Google used evolutionary methods to basically try out different architectures for an artificial neural network. How was it reported in the media? AI creates its own child artificial intelligence breakthrough with this like image of like this baby there or something. Well, if you look at the code, it's basically just a for loop of perturbed things. And yeah, there's a lot of hype out there that I think is not really warranted. So, and finally, this is the part, sadly, that suffered the most from cuts, is I want to highlight a few emerging alternatives and paths forwards. I only really basically just splatter a couple names onto you that are worth Googling. So let's just get started. Some of the things also worth mentioning that are not my goal is I don't want to talk about solved problems, such as the exploding vanishing gradient. Okay, depending on who you ask, you can argue if this is solved or not. But for the concept of this talk, I don't find it that interesting. I will also not talk about AI safety, which is a shame because it's a really interesting, I think, a very important topic. Basically, if we have an AI system, how do we guarantee it actually works in a way we want it to? How does it actually act in a safe way, especially reinforcement learning, thinking about controlling robots and the like. This is a huge topic. It deserves its own talk, its own course, its own study, lifetime spent. So I won't be talking about that. And really importantly, I'm not saying deep learning isn't useful. It's incredibly useful. It's a very powerful technique. You can do incredible things with it, and I would be stupid to say otherwise. But this is something, this is going to be really satisfying for me to finally say in front of people. This is something I wish I could do in front of like half of the AI community and in front of like all of the pop tech, pop media side of the world. Just get to finally say this. Backprop is not how the brain works. This is incredibly important. I hear this so often, especially in the media, where it's like, new startup uses technology inspired by the brain to create new breakthrough. And each and every time it's just a convolutional neural network. It's this backprop, and especially artificial neural network. Our artificial neural network, that word alone, I think is maybe the worst misnomer in the history of technology. I hate it. It's a terrible word. Because if you look at what's going on inside of an artificial neural network as we use it for deep learning, it's not how the brain works, not even close. It's how we thought the brain maybe worked in the 1950s. Our knowledge of these things has expanded dramatically. And no one really ever thought backprop was really how the brain works. Like some people have some theories about it, but it seems incredibly unlikely or even impossible. So basically, this is the heart of the talk this year. Is that a lot of people, when they hear AI, they think of brains, they think of humans, they think of how we think, how we process, our weaknesses, our strength. And this is a big problem because it can give us a very wrong image of what these algorithms are and what they're actually doing. So I want to give you a little bit of an intuitive feeling for this. So let's do a little bit of an experiment here, all of us here together. So this is a xenophyophore. It's a really interesting kind of creature. It's like this big, but it's actually one cell. This is actually a one-celled organism. Weird, right? There's lots of weird shit in the world. Okay, so who here, before me telling you about it, has ever heard of or seen a xenophyophore? Okay, 1 or 2 people. I'm impressed. But the rest of you, and you've never really gotten any information other than what I've told you and this one image here. So okay, let's do an experiment here. I'm going to ask you a couple questions, and you just raise your hands if you think yes, or leave your hands down if no. So, is this a xenophyophore? Just guess, yes or no.
What do we do?
Hands if yes, down if no. Okay, all right. How about this? Is this a xenophyophore? All right. Is this a xenophyophore? All right. Is this a xenophyophore? All right, that's pretty interesting. Well, okay, let's, a couple other questions. Do xenophyophores have arms? Okay. Can xenophyophores run really fast? Do xenophyophores live in deserts? Do xenophyophores live underwater? All right. Well, that's kind of curious. You were able to identify new images of xenophyophores and even answer questions about them without having seen 500,000 training examples. Well, that's weird. Well, anyone that knows deep learning knows where this is going. Sample inefficiency. This is like one of the biggest problems with deep learning, and one of the most interesting problems in my opinion. The deep learning needs a lot of data to work, compared to at least what a human might need. Like you saw one image of a thing you knew nothing about, and you could already answer questions about it and identify new images. That's not something you could get a neural network to do, as hard as you try. So yeah, this is the news to anyone who knows deep learning. I find this problem, though, actually is even more interesting than just an engineering problem. Because you might say, okay, well, we just make bigger data sets. That fixes our problem. Not necessarily. And that's why I find it very interesting. Same problem kind of moves on and evolves into more deeper, interesting problems. And I wish we had time to talk about like information theory and stuff like this, which I think is a really interesting part. But there are other problems with this kind of data inefficiency, with things such as edge cases and generalization. Like, imagine a red xenophyophore. You've never seen a red xenophyophore, but you could still easily visualize one. And if I showed you a picture of a red xenophyophore, you could easily tell what it is. While even state-of-the-art neural networks can be confused by stuff like that, or just flipping the image around or stuff like that. They at least have huge lowering in precision. This doesn't happen to you, and would be a property we would like our neural networks to have. An even more interesting problem, especially for AI people like me, is this concept that if you train a neural network to do one thing, it's hard or almost impossible to train it to do something different. This is a perfect example also is you just have less data for one class than other class. Like say you're training a neural network to identify 1,000 types of images. And for one class, you have only 1% as much data as for the other. Your network is going to have huge problems identifying that object. This is just because of how the algorithms work. Even so, I showed you 1 or, well, 3 pictures of xenophyophores. And you already now have a pretty solid understanding of what they are or what they look like. This leads into this really interesting problem of catastrophic forgetting, which is especially interesting in the reinforcement learning, in the more general AI scope. Is you train it to do one thing, and then you try to teach something new, and in the process, it basically always will forget how to do the first thing. This is an incredibly difficult problem that really, really smart people have worked on a lot, and still is nowhere close to being solved. And it may actually be unsolvable. It'd just be a problem with how neural networks are built and how the algorithms work. So, those are some of the really interesting problems. And now let's get into one of the other very interesting problems I want to talk about today. Okay, just someone shout out, what do you think this is? Just someone. Okay. Yes, something of that. Okay. So what do you think this is? Okay, you say the same thing? Well, sadly, you're wrong. This is a temple, this is an ostrich. Well, okay. According to a state-of-the-art neural image recognition network, that is a temple and that is an ostrich. This is what's called adversarial examples. Basically, you take an original input of some kind and modify it in just a teeny little way, just this weird random noise, and the network becomes incredibly confident in some completely different output. You can see how this could be a big problem, especially in production systems that users give input to. And it gets even worse. This is even possible in the physical world. This is an example of a 3D printed turtle, and it's pretty obviously a turtle. That is actually, someone's artificial intelligence among us, that is very accurately classified as a rifle from almost all angles. This is, I don't have to tell you why this is scary. It could be difficult, for your production environment, or God forbid, if these neural networks ever make their way into automated weapons platform, God forbid. But I want to talk about less about the ethical problems here and more, what does this mean? What is this? Human vision isn't perfect. I'm not trying to say that. The problem of reverse optics is inherently undefined. Reverse optics, what I mean is optics is given an input of light sources and objects, find out what image it projects, and reverse optics is the other way around. Given an image, find out what objects and light sources created that image. And there's literally an infinite amount of possible combinations for every input. So it's never perfect. This is his favorite duck rabbit, where you see a duck, but then you kind of see a rabbit, or you see a duck, or you see a rabbit. It's like a flaw, a bug in our human processing system, just the way we perform reverse optics in our brain. And so there are different failure modes, and some of them we share with these artificial intelligences. The obvious one is just the ambiguous photo. Is this a crab or a pizza? I can't tell. I don't know. And it's more that the image doesn't contain enough information for me to be really sure what it is, to really truly disambiguate. So, if the neural network messes up on this image, it's understandable to us. The second one, where it gets messed up because there's multiple classes within one image, I see that more as an engineering problem. That you just have to design your networks to be able to give multiple outputs, basically. The last ones, though, these adversarial examples, that is something that is truly unique to deep learning gradient-based neural networks. This is something that does not happen in humans. But that would be a great writing prompt for a next sci-fi horror story, adversarial examples that work on humans. That would be interesting and terrifying. So why I'm talking about this is not, well, first of all, just to make you aware this exists, the cybercrime implementation, that I'm telling you, this is going to be a big thing in cybercrime in the next 5 to 10 years, where more and more companies are using deep learning in their pipeline, and you can see criminals using this to exploit those pipelines. This is going to happen. But why I find it really interesting for this talk is that we really like to humanize what deep learning networks are doing. Oh, well, the first layer is the extract edges, and the next one's more complex forms. But we have the data, we have the science. It's not true. That metaphor is wrong. It is not just a bad metaphor, it is fundamentally wrong. The things that deep learning networks do, the things they compute, are fundamentally different from what our brain is processing, and we can't humanize them this way. If we do, if we humanize them, we will make mistakes and misinterpret what they're capable of, where they fail, where they succeed. And this is a great example of it, where there is no intuition behind it. I can't explain intuitively what is happening. I have a hypothesis to why this is happening, and it doesn't happen in the human brain, though I don't have nearly the math skills to be able to prove it in a paper yet. But fundamentally, there's no intuitive explanation why this is happening or why these things exist. So, okay, that was just a really quick breakdown of some of the, I think, most interesting problems. So what am I saying? Throw it all out? Well, no, of course not. That would be silly. deep learning is one of the big important things is that it's industry ready. Deep learning right now in your company, in your project, can do great things, can create great value, can do really complicated things. It's incredibly powerful, but it's not that powerful. And by that powerful, I mean what the local startup is telling their investors powerful. It's not. It is a technique with ups and downs like any other that has problems, that can do some things really well and just cannot do some other things that maybe our brain is capable of. This is a very telling graph in my opinion. This is from a Kaggle survey last year of the most commonly used techniques. And as you see, deep neural networks actually only make it in 4th place, which is still respectable, don't get me wrong. Like if you want to do image recognition, you have to use convolutional neural networks. I mean, there's nothing that even comes close. It's just fact. But even here, we see the top ones are stuff like logistic regression, decision trees. Very, very simple techniques that still provide enormous value and do very important things. If I remember correctly, even like the most effective algorithm on Kaggle by wins is actually, I think, boosted gradient trees or something like that. So also a comparatively simplistic statistical technique. So this is the part of the talk that suffered the most. I'm just going to basically tell you some really interesting things that are worth looking into if you're interested in this kind of stuff, not interested in what works right now today, but what might work in 5 years or in 10 years, and maybe make things possible that currently just are not doable. So this isn't really a departure too far from what we're currently doing, called synthetic gradients, which I find a really interesting idea that I'm surprised not more people are looking into. The idea is basically it breaks away from backpropagation and allows you to train your neural networks without having to perform a backpropagation through the entire thing. You kind of estimate the gradients on a per layer basis, which is much more computationally efficient and has other really interesting properties. But it doesn't really provide a solution. It's still gradient-based learning at the heart. Another interesting thing that's becoming more and more popular, especially in the big companies like Google and Uber, is evolutionary strategies, so using evolutionary algorithms to train or build your neural networks. This doesn't fully break away from the paradigm because it's still usually used to evolve normal artificial neural networks. Theoretically, it could be used to evolve anything. I mean, there's no limit to it, but this is what's mostly done. And it's having some really impressive results. It seems, I mean, currently it seems to be as effective deep learning, at least maybe a little bit more efficient, but costs a lot more computation, at least how things currently look. I want to give a special mention to a really interesting technique called novelty search, which I think is kind of like another thing that's not getting as much attention as it should. The idea is instead of having your evolution maximize for fitness, it maximizes for novelty. So your network doing something interesting, something different. And while it seems really counterintuitive, empirically, there's been quite some data showing that it actually can lead to better and more ultimately more efficient and strong results by looking at more different like functional space. Very early work, but very interesting. I want to give a shout out to probabilistic programming, which isn't really kind of sort of a machine learning technique depending on how you use it. I just kind of want to mention Josh Tenenbaum at MIT because I think his work is really, really interesting. Because what he does is he studies small children, very, very young children, and how they learn concepts around them, how they learn how physics works, how they learn how objects interact, stuff like that, and he tries to model that progression and the biases that those children have in these kinds of probabilistic programs to give a better algorithmic understanding of what our brain might be doing, and then how maybe we could apply these kinds of models to real-world problems. It's interesting. Then there are two biologically inspired methods I would like to mention. There are dozens, if not hundreds, of biological brain models, most of them of very small parts of the brain. There's also the really big projects like the Blue Brain Project and stuff. Not going to really mention them because they're in early stages and kind of scientifically dubious to some people. It's kind of interesting controversy going on there right now. So the two like big models that actually do something I would like to mention are Hierarchical Temporal Memory by Jeff Hawkins mostly and his company Numenta, and the BioSpawn model by Professor Leah Smith at the University of Waterloo. I find these two very interesting, and especially Hierarchical Temporal Memory. BioSpawn is a really interesting concept because it's basically a full brain model. It models very many parts of the brain, and it can do lots of different tasks without catastrophic forgetting. It can learn many tasks, reinforcement learning tasks, supervised tasks, different tasks, without forgetting previous tasks, and can still perform them very well in a close to biological way. There are some problems with the model, I think, that still need to be addressed, figured out, but it's definitely interesting. If anything from this talk, I would just love to shill a little bit for hierarchical temporal memory, which is my personal favorite for like the unappreciated, interesting algorithm going on right now. It's really interesting that the HTM algorithm actually is getting a lot of attention in the neuroscience community, but very little in the machine learning community. And I'd like to do my little part to change that, because unlike many others, it is actually already a feasible algorithm. It's on GitHub. You can get it. You can play with it. It can already do interesting things. It can't do everything. It's not perfect. It's a work in progress model of the human neocortex, the smart part of our brain. So that is completely different. It's very, very different from artificial neural networks. It works at things very, very differently in very, very elegant ways. It has a lot of really interesting properties. I'd love to talk about, I don't know, afterwards or something if we have the time. But, well, in closing, let me just put together what I wanted to say here. The brains and its neurons are extremely complex. We shouldn't expect them to be calculating some simple algorithm. And let's face it, backpropagation and artificial neurons are very simple algorithms. They're very simple linear algebra, very simple calculus. They're not very fantastically sophisticated. Of course, yes, RNNs are universal function approximators, et cetera, but still, it's worth keeping in mind. Deep learning is very powerful. It's useful and it's industry ready, but it is overhyped in some ways. There are some things that deep neural networks just cannot do. Like a favorite example is just robot movement. You've all seen the Boston Dynamics like robot movement videos of the anthropomorphic robots being able to like jump or walk through a forest without falling over. They don't use deep learning, like for nothing. They even kind of talked some smack about it a few times because it's just not there. There's just problems with these algorithms that currently cannot be overcome in this way. The message I want to deliver to you, and that I hope you can all internalize, is that we need to do our best to not humanize or even deify deep learning. It is a very powerful algorithm. It's very useful. It can do very useful things, but it's not the be-all, end-all of AI. There's going to be a next big thing. There's going to be some algorithm that's better. There's going to be some approach that does things better or that fixes the problems. For the moment, we just have to keep in mind what it's good at and use it for that, and be aware when it perhaps is not the best solution. Thank you.
Yeah, thanks a lot, Connor, for this amazing talk. Do we have questions on the brain?
Sure.
Could you actually expand a little bit further on that favorite moment?
Oh, I could expand on that for hours, actually. The hierarchical temporal memory is a really fascinating concept, and because it is very close to biology, but it's from a computer science perspective. Jeff Hawkins is definitely computer science at heart, and he wants to find out how do we model synapses, how do we model electrochemical situations, what is the algorithm that these neurons are processing? He says, okay, neurons are processing elements of some kind. What are they doing? What is the calculations they're doing? And he's been working on this for decades at this point. He wrote a really interesting book called On Intelligence about 10 years ago, which to this day I recommend. It's really interesting because he makes a lot of interesting predictions about what the brain must be doing. And this is basically his attempt, bit by bit, to make progress in this. The most important difference with artificial neural networks is the concept of what he calls sparse distributed representations, which is really, really interesting. I think that's the heart of the model. That's the most interesting thing. There's a lot of other really interesting things in this model, but I think this is the most interesting idea. The idea is instead of modeling things as real numbered vectors, you model them as very, very high dimensional binary matrices, where every one has a semantic meaning. So I think a lot of the problem, actually, personally, I think perhaps stuff like adversarial examples is because we model things in a continuous fashion within deep learning, while the brain, it's spiking. There's either action potential or no action potential. It's a binary representation, and this has lots of really great properties, like fault tolerance. Like if you can knock out 40% of those neurons and it'll still work without a problem. It has properties like being very easy to generalize, because I can create a union between two matrices to create whatever that is. So I could take the matrix for red and the matrix for xenophyophore, combine them, and I have the matrix for red xenophyophore, and it can scale that way. That's what I think is the core really interesting idea, to look at data kind of as a different way, as a semantic representation. How it actually processes this thing is a longer talk. We can talk later if you're interested.
I think there's a lot of potential also for fault lines.
Mm-hmm.
Further, yeah.
But are there papers out there that say, okay, based on this evidence that we observe, backpropagation is not implemented in some form in the brain?
That's a very good question. This is something I definitely want to talk about. Well, there's one big problem with backpropagation. Backpropagation, if you look at it, is basically a supervised algorithm. You need a supervisor that has a view of the entire network, that can backprop the errors throughout the entire thing. There is basically no proof that something like this exists in the brain. The brain seems to have what's very Hebbian learning rules, very local rules, that local clusters of neurons do influence each other, but they very rarely only lightly influence neurons wide away. There's not one center master learner that computes the gradients for each part. Now, on the other hand, there are some theories about more local versions of grade, like these synthetic gradients, which could be implemented. And there actually is some really compelling evidence that one part of the brain actually does implement backprop. The so-called cerebellum, the small part of your brain back there, has certain neurons and properties that are suspiciously close, actually, to artificial neural networks in their shape and the way they learn. But these are very different from the neurons you see in the neocortex, so the big wrinkly part of your brain. The properties you need to implement backpropagation seem just to not exist in the brain. The brain is wet, it's messy, it's very local, things kind of go in all directions, neurons do their own thing. And also if you look at stuff like firing together wires together, which is the basis of the rule, that doesn't exist in backpropagation. So there could be stuff like this going on. I think it's probably that there's not one algorithm running in the brain, but many, many different kinds that kind of supplement each other's in a different way. One of them might be backpropagation or a variant thereof. I'm especially convinced possibly that the cerebellum is implementing something like this, but it seems obvious also because the human brain doesn't have the same weaknesses as these algorithms do, that it can't be the end-all, be-all. Because if it was, then shouldn't we be vulnerable to adversarial examples?
One more question in the back, yeah? In the third row from the front. You, yeah.
Yes,
Yeah.
so I was going in the same direction. It was basically, do you think neural networks are a better idea or just backpropagation?
I would say they both cause different problems, but but both is basically my point. Is that backpropagation is, if you look at it at its heart, it is a statistical numerical optimization method. It's not meant to simulate biology. It's not inspired by biology, at least not directly. It's a mathematical optimization method. It's good for that. I'm not saying it's wrong, it's bad or something, but mostly I'm trying to fight this concept that these algorithms are close to biology and that we can expect them in this way. I would be personally very, very interested what would happen if you take neural networks and train them in very, very different ways, if they have these same weaknesses or not. I would find that interesting. But either way, I think no matter which of these parts we use, we're not going to get to biological intelligence, at least not directly, if we use either part. We need other parts of some kind.
Okay, maybe last question. Yeah.
Is there any known way that the brain can backflow information?
Yeah, like for example, in the cerebellum, there's what's called, oh God, I hope I'm saying this right. I hope I'm remembering this. It's climbing fiber neurons, if I remember this correctly, which are specialized neurons that basically say I want to grab a glass of water in front of me, and I move my hand to grab the glass. If I miss it, these neurons fire. They recognize that I failed to get it, and they fire. This has been measured many times. And that goes directly to the cerebellum, which is related to movement processing, and seems to be a kind of error signal. And if you look at the cells in the cerebellum, especially these so-called Purkinje cells, they're basically very dense, like small cells with lots and lots of connections that look suspiciously close to artificial neural networks. So there is quite some evidence to show that the cerebellum may be implementing backpropagation or some kind of error correction kind algorithm. But it seems unlikely, and I mean, there's definitely some kind of, error learning in other parts of the brain, but it seems unlikely to impossible for something, especially the supervised, to exist in other parts of the brain, especially when you go to way more abstract kinds of thought. It seems very likely that or even proven, depending on who you ask, that the main part of the brain, the neocortex, is some kind of unsupervised algorithm. It's completely unsupervised. It doesn't need a learning signal necessarily, because also, like, where would it come from? Like, where would how would it be generated? And if it would be generated, it would probably be more of a reinforcement learning signal than a kind of supervised signal.
Okay, so I think there's a lot of possibility to discuss these things further during the network are fitted.
Yeah, please,
So,
just come right up to me. I love rambling about this stuff for hours.
Voilà.